Assalamu alaikum. Welcome to my channel M.Asif Math Corner. Today we will study about complexes of a group. Let's start. Complexes in a group. An arbitrary subset X of G is called the complex in G. The subsets of G are called complexes of G. The subgroups, we are not talking about the subgroups of G, we are talking about the subset of G. Subgroup and the complex are different. For two complexes X and Y in G, we define their product as complex XY like this. When we multiply X by Y, then their elements will surely multiply with each other, and X belongs to X here and Y belongs to Y. So let little bit explain about complexes. What are complexes? Let take a group G and take some elements iota, minus iota, 1 and minus 1. Here take a complex A of G, let me say that 1 and minus 1 and iota. This set is not the subgroup of G, but it is the complex of G. 1 minus 1 and iota is not subgroup of G, because we know that when we multiply minus 1 into iota, the answer is minus iota, and minus iota is not here, that's why it's not closed. So this is not a subgroup of G, but it is complex of G. So complexes of G we can find in similar way as we find the subsets of set. For example, 1 is a subset of G, means complex of G, and iota is also 1 iota also. We can take 1 separately, and then 2 then 3, as we take the subsets in set theory. See, in similar way, all the subsets of G are the complexes of G. And when we take 2H and K are complexes of G, for example, H is equal to 1, 3 and K is equal to 1, 5, then their product H and K, we have defined that small h and k, where small h belongs to capital H and small k belongs to capital K. Here the H K means the first element of H will multiply by first element of K. This gives us 1. The first these are the subsets of modulo 5 and modulo 8. So 1 multiplied by 1, this one, 1 multiplied by 5, 5, then 3 multiplied by 3, 3, then 3 multiplied by 5, 3 are 15, and 15 divided by, because these are the subsets of modulo 8, so divided by 8 we get 7. In this way we get the product of complexes. Let's have a theorem related to it. The complexes of group, let A and B be the finite subgroup of a group G. Then the complexes AB contain exactly M n divides Q, where M, N and Q are respectively orders of A, B and Q. It means the number of elements in A are M, and the number of elements in B are N, and the number of elements in Q are small q, and Q is equal to the intersection of A and B. So as we have read before that the every intersection of every subgroups, every two subgroups, three subgroups, or many subgroups will also be a subgroup. That's why since Q is the intersection of subgroups of A and B of group G, therefore Q is also subgroup of G. Since A and B are the finite subgroup of G, therefore the order Q of Q and the index R is equal to n divides Q. Hence, because these are the subgroups, so the order of Q will divide n, where n is the order of B and Q is the order of Q. In B is finite. Let's suppose B is equal to all the right cosets of Q of B in Q. B the right cosets. The decomposition of B means that these all right cosets, when we combine, when we take their union, they make complete B. And further condition is then only B1 Bi is equal to E. E means identity element, and other Bi which are greater than 1 does not belongs to Q. So the set BQI is not equal to Q, but their union is equal to B. We are going to prove that the order of two subgroups will be divided by the order of their union, their intersection. AB is equal to A, and we have proved before, we let before that B is equal to all union of right cosets of B in Q. So AB is equal to A into, and we have let that suppose that B is equal to union of all right cosets of Q in B. So here we can write in this way the union of all right cosets of B in Q into A, and since Q is the subgroup of A, because other elements of because we have read here that Bi does not belong to Q. Here it means that it is the Q is the union of A and B. So Q, all the elements of Q contain in A. All the elements of Q contain in A. That's why the Q is the subgroup of A. Therefore, AQ, where A and X belongs to Q, are equal to A, because all the elements contain in A. Since we can write simply that in the AQ we just put A at the place of AQ. So here we have this equation: AB is equal to all the right cosets of B in Q into A. So how many cosets there are right cosets? So as Bi belongs to B and Bi does not belong to Q, which shows that Bi also does not belong to A, because the Q is the intersection of A and B for I is greater than 1. The cosets of AB where I is equal to 1 to R are all distinct, because we have read before that all the cosets are distinct, so their intersection is phi and their union will become the complete group from where we take their cosets. So each of these cosets contain exactly m elements. Because order of A is m, it means that when one multiply all the elements of A, it's become m times 1, and when 2 multiply with a m times 2, it means that all the elements of m are there or times such cosets. So order of AB will be equal to summation of all right cosets of B in Q into A. So we can write it, because these are R, I is 1 to R, so we R times add them, AB1, AB2, AB3, AB4, ABR, and it means that B is R times, so R into A, order of A. The order of A is M, and in start we told that the index R is equal to N by Q. Hence proved that the order of AB is equal to Mn divides Q. Hence the complex AB contain exactly these elements. The complex contain exactly these elements. I hope you understood. Thank you so much.